Welcome to a lesson on hypothesis testing with two samples. Studies often compare two groups. For example, researchers are interested in the effect aspirin has in preventing heart attacks. Over the last several years, articles have reported various aspirin studies involving two groups. Typically, one group is given aspirin and the other group is given a placebo. Then the heart attack rate is studied over several years. There are other situations that deal with the comparison of two groups. For example, studies compare various diet and exercise programs. Politicians compare the proportion of individuals from different income brackets who vote for them. Students are interested in whether SAT or GRE preparatory courses really help raise their scores. We have learned to conduct hypothesis tests on single means and single proportions. We will now compare two means or two proportions to each other. The general procedure is still the same, just expanded. To compare two means or two proportions, we work with two groups. The groups are classified either as independent or matched pairs. Independent groups consist of two samples that are independent, that is, sample values selected from one population are not related in any way to sample values selected from the other population. Matched pairs consist of two samples that are dependent. The parameter tested using matched pairs is the population mean. The parameters tested using independent groups are either population means or population proportions. In this video, we will focus on comparing two population means with an unknown population standard deviation. In this case, the two independent samples are simple random samples from two distinct populations. For the two distinct populations, if the sample sizes are small, the distributions are important, meaning they should be normal. If the sample sizes are large, the distributions are not important, meaning they need not be normal. And below we have the formulas for the standard error. Notice how the test statistic is a t-score. This is because we have an unknown population standard deviation, and here we have the formula for the degrees of freedom. Let's take a look at an example. The average amount of time boys and girls ages 7 to 11 spend playing sports each day is believed to be the same. A study is done and data are collected, resulting in the table shown below. Each population has a normal distribution. Notice how we have the sample size, the average number of hours playing sports per day, and the sample standard deviation. So from the table, let's let x bar sub g equal the sample mean for the girls, which is equal to 2. S sub g, the sample standard deviation, is 0.866 for the girls, and the sample size n sub g is 9. And then for the boys, we have x bar sub b is equal to 3.2, s sub g is equal to 1, and n sub b is equal to 16. We want to answer the question, is there a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day test at a 5% level of significance? So we know alpha is equal to 0.05, 5% is a decimal. Again, the population standard deviations are unknown. We will let mu sub g equal the population mean for the girls and mu sub b equal the population mean for the boys. Because we are trying to determine whether there is a difference in the mean amount of time boys and girls aged 7 to 11 play sports each day, the alternative hypothesis is mu sub g doesn't equal mu sub b, and the null hypothesis is mu sub g equals mu sub b, because if there is no difference, they're the same, meaning mu sub g equals mu sub b. We can also change the form of these hypotheses and state the alternative hypothesis is mu sub g minus u sub b doesn't equal 0, and the null hypothesis as mu sub g minus mu sub b equals 0. Notice how we have a two-tailed test because of the not equal in the alternative hypothesis. The distribution for the test is a student t-distribution, again because the population standard deviation is unknown. We can refer to the t-score as t sub df, where df equals the degrees of freedom, which is approximately 18.8462, which we can obtain by evaluating the formula shown here below. And you may want to verify this. We do not pool the variances. Before we calculate the test statistic, which we now know is a t-score, and the p-value, let's look at this graph here below. Notice x bar sub g minus x bar sub b is equal to 2 minus 3.2, which is negative 1.2. So if the population means are the same, the difference would be 0, which is at the center of the distribution. And then to the left we have negative 1.2, to the right we have positive 1.2. And therefore the p-value is equal to the combined area on the left and right. If we multiply by 1/2, we can find the separate areas, or the area on the left and the area on the right, which means the p-value is also equal to the probability that x bar sub g minus x bar sub b is less than or equal to negative 1.2, or x bar sub g minus x bar sub b is greater than or equal to 1.2. Let's go to the TI-84 and determine the t-score and the p-value. To do this, we press stat, right arrow to tests. We want option 4, two-sample t-test. We press 4. For the input, we use statistics, which I've already selected. Down. X bar sub 1 is x bar sub g, which is 2. Enter. The sample standard deviation, S sub g is equal to 0.866. Enter. The sample size is 9. Enter. And now for the boys, the sample mean is 3.2. Enter. The sample standard deviation is 1. Enter. The sample size for the boys is 16. Enter. And now because the null hypothesis is mu sub g doesn't equal mu sub b, we select a not equals by pressing enter. For pooled, we select no, arrow down again, and we click calculate. So notice how the t-score is approximately negative 3.1424, and the p-value is approximately 0.0054. Let's go ahead and record these. Before we compare the p-value and the alpha, let's talk about the t-score of negative 3.1424. If we were doing this by hand, we would calculate the z-scores for an alpha of 0.05, which I've already done here. Notice the z-scores are 1.96 and negative 1.96. And then if we calculate the t-score by hand, notice how we get negative 3.1424, which we just saw on the 84. And notice how this is to the left of the z-score of negative 1.96, and therefore the t-score is in the rejection region, meaning we reject the null hypothesis. But let's also find the same conclusion comparing the p-value with alpha. Notice how the p-value is low compared to alpha, and if the p-value is low, the null must go, or more formally, because the p-value is less than or equal to alpha, or because alpha is greater than or equal to the p-value, we reject the null hypothesis, which means we reject that mu sub g is equal to mu sub b. The means are different. Our final conclusion is, at the 5% level of significance, the sample data show there is sufficient evidence to conclude that the mean number of hours that girls and boys aged 7 to 11 play sports per day is different. I hope you found this helpful.